It isn't the cold that builds an ice age. That is the first thing to let go of tonight, the first small surprise to carry with you down into sleep. We imagine the great glaciations as a matter of bitter winters, of cold, deepening year on year, until the world freezes over. But that isn't how it happens. Ice ages are not born from cold winters. They are born from summers that come too gently to melt the snow. Think about that for a moment, slowly, the way you might turn a smooth stone over in your hand in the dark. Somewhere in the far north, snow falls through the long winter, as it always does, piling soft and white across the land. Then spring comes and summer after it, and the sun climbs a little higher, and the snow begins to melt. In an ordinary year, it all melts away. The land goes green again. The cycle resets, and nothing is left over. But imagine a summer that is just slightly too cool. Not dramatically. Not a frozen summer of frost and storm. Just a summer where the sun is a touch weaker, where the warmth arrives a little softer than usual, and a thin skin of last winter's snow survives into autumn without melting. It lingers in the shadowed places, in the high valleys, on the cold slopes that face away from the light. And then the next winter comes and lays more snow on top of what remained. And the summer after that is gentle too, and again a little is left behind. Year after year, summer after gentle summer, the unmelted remainder grows. The snow compresses under its own weight into ice. The ice thickens and spreads and begins to flow. And given enough of those gentle summers, enough centuries, enough millennia of warmth that comes too softly to undo the winter's work, you get a sheet of ice a mile thick lying across Canada and Scandinavia and the north of Europe. A continent buried, a world remade. All of it beginning not with a great cold, but with a summer that simply forgot to melt the snow. That is the secret at the heart of the ice ages, and it is the thread we are going to follow tonight, slowly, all the way down. It is one of those truths that feels almost too quiet to be true. The largest slow event the planet's surface knows, the burying of whole continents under ice, and the trigger is not violence at all. It is a softness, a gentleness in the summer light. So now hold this beside it, because it makes the whole thing stranger still. The amount of sunlight Earth receives across a year barely changes. Over the long, slow turning of the orbital cycles we are going to spend this night exploring, the total sunlight reaching the planet flickers by only about 1 part in 1,000, about 1/10 of 1%. That is the whole signal, that is the entire push from the heavens. A flicker of sunlight too small to feel on your skin, too small for any creature to notice in a single lifetime, too small to register against the ordinary swing of day and season. And yet that whisper of a change is enough, over tens of thousands of years, to decide whether a mile of ice buries the northern world or whether the land lies green and open beneath the sun. A whisper that moves continents. Hold that image as we go. A change in the light so faint you could never feel it, and at the other end of that faint change, glaciers grinding south across what is now New York, what is now London, what is now Berlin. The smallest cause you can imagine, tied to the largest effect the surface of the world can produce. That gap, that strange and enormous gap between the gentleness of the trigger and the vastness of the result, is one of the most beautiful puzzles in all of science. And by the end of these long hours together, you will understand how that small flicker becomes a continent of ice. You will also understand the parts that even now, even after 1.5 centuries of patient work, no one has fully solved. Because this is not a tidy machine with all its gears explained. It is a real mystery, still partly open. And that is exactly why it is such good company for the journey into sleep. Before we begin the long descent, let me ask you something gently. the way you might be asked by someone sitting near you in a quiet room. Tell me where in the world you are listening from tonight. What window is dark beside you? What city or hillside or stretch of countryside holds you while you drift? Leave it in the comments if you feel moved to, sometime when you are awake again. It is a strange comfort, this, to think of all of us scattered across that same northern world and the southern one too, lying in the dark, listening to the same slow story about the ice. And if you are new here, and you would like more nights like this one, more slow journeys into the deep workings of the world told quietly enough to fall asleep inside, then subscribe and they will keep coming. Now, settle in. You do not need to follow every thread. You do not need to remember the numbers or hold the names or stay awake to the end. The whole point of tonight is that you may drift off at any moment, anywhere along the way, and lose nothing, because there is no test and no finish line, only the slow unwinding of a true and patient story. Let your breathing slow. Let the weight of the day go out of your shoulders. We are going to go down gently into one of the oldest and strangest clockworks in the world, the clockwork that decides when the ice comes and when it goes. And to understand it, we have to leave the surface of the Earth entirely and rise up and look at the planet from far away, where it becomes a small blue thing turning in the dark, tracing its long path around the sun. Because the answer to why the ice comes and goes is not written in the weather, or in the wind, or in the oceans alone. It is written in the shape of Earth's journey around the sun, and in the slow, patient wobbling of the planet as it spins. There are 3 of these motions, 3 great slow wobbles, each turning on its own enormous span of time, each almost imperceptible from one year to the next, and together they decide, across the ages, how much summer sunlight reaches the far north. 3 wobbles that decide when ice ages begin. Let us meet them one by one, slowly, in no hurry at all. The first is called eccentricity, and it is the shape of Earth's orbit. We tend to picture the planets circling the sun in neat, perfect circles, the way they are drawn in a child's diagram. But that is not quite true. Earth's orbit is very nearly circular, but not exactly. It is slightly stretched, slightly oval, the way a circle would look if you took it gently between 2 fingers and pulled just a little. The measure of how stretched it is, how far from a perfect circle, is what astronomers call eccentricity. A perfect circle has an eccentricity of 0. The more drawn out and elliptical the loop becomes, the larger the number grows. Right now, today, Earth's orbit has an eccentricity of about 0.0167, a tiny number. It means our orbit is very close to a circle, only faintly stretched. You would not notice the difference by eye if you saw it drawn, but here is the slow magic of it. That number does not stay fixed. Over enormous spans of time, the shape of Earth's orbit breathes. It stretches and it relaxes, drawing out into a more pronounced oval, and then easing back toward a near-perfect circle, over and over on a rhythm of roughly 100,000 years, and a longer, deeper beat of about 405,000 years laid beneath it. At its most circular, the eccentricity drops to around 0.0034, the orbit almost a true ring. At its most stretched, it climbs to around 0.058, the loop more clearly drawn out into an ellipse, and then back again. Stretch and relax and stretch across the slow tens of thousands of years. And what does the stretching? What hand reaches out and pulls Earth's orbit gently into an oval and then lets it ease back? It is the other planets, mostly 2 of them. Mighty Jupiter, the giant of the solar system, with its great gravitational pull, and Venus, our near neighbor, close enough to tug at us as it passes. The 2 of them, The heavy giant far out and the bright neighbor near in reach across the empty space with their gravity and slowly, patiently, over thousands upon thousands of years, knead the shape of Earth's path around the sun. We feel nothing of it. We carry on season after season, while far away the great planets stretch and relax our orbit on rhythms longer than any human memory could hold. That 405,000-year beat in particular is so steady, so reliable, so faithful across the ages that we will come back to it later in the night and find that it can be used as a kind of clock to read the age of rocks hundreds of millions of years old. But that is for later. For now, simply hold the picture. The shape of Earth's orbit, breathing slowly between a near-perfect circle and a gentle oval, kneaded by the distant hands of Jupiter and Venus. That is the first wobble. Eccentricity. The second wobble is the tilt of the world, and it has a name almost as old and heavy as the thing itself. Obliquity. The Earth, as you know, does not spin upright as it circles the sun, it leans. Its axis, the invisible line running from the North Pole to the South Pole around which the planet turns, is tipped over at an angle. It is this tilt that gives us our seasons. When the northern half of the world is leaned toward the sun, the north has its summer, the days long and the light direct. Half a year later, when that same hemisphere is leaned away, it has its winter, the days short and the sunlight slanting low and weak. The tilt is the reason the year has a shape at all, the reason there is a warm season and a cold one, the reason the snow falls and the snow melts. Right now, today, the Earth's axis is tilted at about 23.44 degrees from upright. And here, again, comes the slow magic. That tilt is not fixed, it nods. Over time, the angle of Earth's lean changes, oscillating slowly back and forth between roughly 22.1 degrees at its most upright and about 24.5 degrees at its most pronounced. Not a large swing, a little more than 2 degrees from one extreme to the other. But it matters enormously because it changes how strong the seasons are. When the tilt is greater, nearer 24.5 degrees, the seasons grow more extreme. The summers are hotter because the leaning hemisphere is turned more directly toward the sun. The winters are colder because the other half is turned more fully away. And this happens in both hemispheres at once, north and south together, since it is the whole planet's lean that has steepened. When the tilt is smaller, nearer 22 degrees, the seasons soften everywhere. The summers a little cooler, the winters a little milder, the whole year gentler in its swing. This nodding of the tilt completes itself on a rhythm of about 41,000 years. 41,000 years to go from one extreme of lean to the other and back again. And right now, our tilt of 23.44 degrees is slowly decreasing, easing very gradually back toward the more upright end of the range, which means, all else being equal, that the planet's seasons are very, very slowly softening, summer by summer, over spans of time so long that no person, no nation, no civilization could ever watch it happen. That is the second wobble, obliquity, the slow nodding of the world's tilt between 22.1 and 24.5 degrees every 41,000 years, deciding how fierce or how gentle the seasons are. And remember the secret we began with, the cool summer that fails to melt the snow, and you can already feel why this matters. A smaller tilt, a gentler summer in the north. And a gentler summer is exactly the kind of summer that lets the snow survive. The third wobble is the strangest and the most beautiful to picture, and it is called precession. To understand it, think of a spinning top, the kind a child sets going on a table. While it spins fast, it stands nearly upright. But as it turns, you will notice that the top itself does something slower than its own spinning. Its axis, the line through its center, traces a slow circle in the air. It leans, and that lean itself rotates around, sweeping out the shape of a cone, while the top goes on spinning quickly beneath. The fast spin is one motion. The slow circling of the tilt is another laid over it. The Earth does exactly this. It spins quickly once a day, giving us day and night. But its axis, its tilt, also traces a slow circle in space, sweeping out a great cone over an enormous span of time, just like the wobble of the spinning top. This is precession, and the time it takes for Earth's axis to complete one full circle of that cone to wobble all the way around and return to where it began is about 25,772 years. Nearly 26,000 years for the axis to trace one full slow loop in the sky. It is why over the ages the pole star changes. The star our axis points to today is not the star it pointed to thousands of years ago, and not the one it will point to thousands of years from now. The whole sky's center of turning drifts slowly around on that 26,000-year wobble of the leaning Earth. But precession does something even more important for our story than moving the pole star, and to see it, you have to bring together two of the wobbles at once. The tilt is what gives us seasons. The orbit, the eccentricity, is the stretched loop we travel around the sun. And because the orbit is stretched even slightly, there is a point in the year when Earth comes closest to the sun and a point when it is farthest away. The closest point is called perihelion. The farthest is called aphelion. They are not dramatic differences in distance, but they are real. And here is the question precession answers. Which season are we having when we pass closest to the sun? Is it summer in the north when Earth is nearest, the warm season, made warmer still by the closeness? Or is it winter in the north at the closest pass, so that the cold season is softened by the extra nearness while summer falls at the far point? The answer drifts slowly because the axis wobbles and because the orbit's own ellipse turns as well, and the two together change which season meets the sun's closest approach. This is the part of precession that matters most for the ice, and it is sometimes called climatic precession, because it is about which season aligns with perihelion. When you combine the wobble of the axis with the slow turning of the stretched orbit, the rhythm that matters for climate works out shorter than the 26,000-year wobble alone. It clusters around two beats, one near 23,000 years and one near 19,000 years. On those rhythms, the Earth slowly trades which hemisphere gets its summer at the close pass, and which gets it at the far one. Today, as it happens, the northern hemisphere has its winter when Earth is nearest the sun in early January, and its summer when Earth is farthest away. We will return to what that means and to the fact that about 11,000 years ago it was the other way around, later in the night when we look closely at the trigger. For now, simply hold the picture of the spinning top, the Earth wobbling slowly on its axis, tracing its great cone across nearly 26,000 years, and in doing so slowly deciding which of our seasons stands closest to the fire of the sun. That is the third wobble. Precession. So now you have met all three. Eccentricity, the slow breathing of the orbit's shape between a near circle and a gentle oval on rhythms of 100,000 and 405,000 years, needed by Jupiter and Venus. Obliquity, the nodding of the world's tilt between 22.1 and 24.5 degrees every 41,000 years, setting how fierce the seasons are. And precession, the wobble of the spinning Earth, tracing its cone every 26,000 years on the climatic rhythms of 23 and 19,000 years, deciding which season meets the sun's closest approach. Three motions, three vast, slow, silent wobbles, each turning on its own great wheel of time, each far too gradual for any creature to feel, and each one quietly altering, century by century, how much summer sunlight falls on the far north of the world. That is the whole orchestra, 3 instruments, each playing a note so long that a single beat of it outlasts every empire that has ever risen and fallen. 100,000 years, 41,000, 23,000. Lay them over one another, and you get a slow, shifting chord, a music played in light across the high latitudes of the earth, swelling and fading over the ages. In some long stretches, all 3 instruments lean the same way at once, weakening the northern summer together, and the chord falls dark, and the snow begins to survive, and the ice begins its patient march. In other stretches, they pull against one another, and the summers stay strong, and the ice melts back, and the world breathes warm and green. The 3 wobbles, rising and falling, weaving their long, slow chord across hundreds of thousands of years, and at the far end of that faint music, continents buried in ice, or continents set free. And remember, through all of it, how small the actual signal is. The total sunlight reaching the Earth changes by only that 0.1% across the whole cycle. The 3 wobbles do not turn the sun up and down like a great furnace. They are not powering the ice with heat withdrawn and heat returned. They are doing something subtler and stranger than that. They are not so much causing the ice as keeping time for it, setting the beat, telling the Earth when. And what the Earth does with that whispered cue, how a flicker too faint to feel becomes a mile of ice, is the deeper mystery we will sink into as the night goes on, slowly, gently, in no hurry at all. But to feel the full weight of why these 3 wobbles matter so much, we have to leave the wide view of the orbit for a while and come back down toward the surface, down to a single, invisible line drawn across the top of the world. Because the whole vast clockwork of the heavens, the breathing orbit and the nodding tilt and the wobbling axis, all of it comes to bear on one particular place, not everywhere equally. One line of latitude running across the cold lands of the north, where the fate of the ice is quietly, patiently decided, summer after gentle summer. That line is 65 degrees north. Draw it on a globe and it passes through the great cold shoulders of the world, across northern Canada, through the middle of Scandinavia, along the wide, silent reaches of Siberia. There is nothing to see there that announces its importance. No marker, no monument, just tundra and forest and the slow rivers, the same low light that has fallen on those latitudes for as long as there have been latitudes at all. And yet it is here, along this faint and arbitrary-seeming line, that the planet makes up its mind about ice. The reason is the one we touched a moment ago, the cool summer paradox, and it is worth letting it settle in fully, because everything else hangs from it. We tend to imagine an ice age beginning with cold, with some terrible deepening of winter, the cold pressing harder and harder until the world freezes over. But that is not how it works. Winters in the far north are already cold. They are cold enough. Adding more cold to a winter that already buries the ground in snow changes very little, because the snow is going to fall either way. What matters, what truly matters, is what happens to that snow when the warm season comes. In an ordinary year, the summer arrives and melts the winter's snow away. The white retreats, the dark ground drinks the sunlight, the land warms, and by the time the cold returns, there is bare earth waiting to receive the next fall. The books are balanced. What came down in winter goes away in summer, and the ice never gains a foothold. This is the world we live in now, the warm pause, the long exhale. But imagine a summer that comes too gently. A summer where the sunlight at 65 north is just a little weaker than usual, weak enough that some of the winter's snow does not melt. A patch survives into autumn. And then the snow falls again on top of it, And the next summer is gentle too, and a little more survives. Year after year, snow upon snow upon snow, none of it fully melting, each layer pressing down on the one beneath until it compacts into ice. That is how an ice age begins, not with a violent freeze but with a failure to melt, with summers too mild to undo what the winter has done. The cold winter builds nothing on its own. It is the cool summer, the summer that came too softly, that lets the ice begin to climb. And so the three wobbles matter for exactly one reason. Not because of what they do to the year as a whole, but because of what they do to that single, decisive northern summer. Obliquity, the nodding tilt when it leans toward its greater angle, throws more summer sunlight onto the high north, and the snow melts and the ice retreats. When it relaxes toward its lesser angle, the northern summers cool and the snow lingers and the ice gathers itself. Precession, the wobbling axis, slides the seasons around the orbit, deciding whether the northern summer falls when the Earth is near the Sun or far from it. And eccentricity, the breathing shape of the orbit itself, governs how much those near and far positions even matter, stretching and slackening the whole effect. Three slow movements layered one over the other, and where they meet, at 65 north, in the warmth or weakness of a single season, the ice is told whether to grow or to die. There is one more piece to this, and it explains why we keep speaking of the north, always the north, and almost never the south. Because the Earth is not symmetrical. Look at the top of the globe and you find land, vast continental land, the great spread of North America, and the long reach of Eurasia, sprawling across exactly those latitudes where the summers are decided. Land can hold ice. A continent gives the snow somewhere to settle and pile and harden, somewhere to build itself into sheets a mile and more in thickness, sheets that can sit and grow and endure across the long, slow turning of the cycles. Now look at the bottom of the globe at the same latitudes in the southern hemisphere, and you find something else entirely. Ocean. Open water, the great southern ocean, circling the world without a continent to interrupt it. And the ocean will not hold an ice sheet the way the land will. Water moves, water mixes, water carries warmth from elsewhere, and resists the patient stacking of frozen years. So even when the southern summers cool, there is no broad northern-style land for the ice to seize. The geography simply will not allow it. The fate of the ice is decided in the north, not because the north is favored by the heavens, but because the north is where the continents happen to be, an accident of where the land sits on the turning globe, and from that accident, an age of ice, or its absence. So hold these two things together as we drift on, the faint signal from above the 0.1%, the three wobbles keeping their slow time, and the place where that signal lands, this one line across the cold continental north, where a gentle summer can let the snow survive its first year, and a second, and 100th, until the survival of snow becomes a sheet of ice that buries Canada and presses Scandinavia down into the sea. The whisper from the sky and the patient continent that listens. If you are drifting along with me through all of this, somewhere out there in the dark with your own window of cold or warmth beyond the glass, I would love to know where in the world you are listening from tonight. Leave it in the comments if you feel like it. A single word, the name of your town or your country, somewhere along your own line of latitude. And if you are new here and you would like more of these slow journeys into the deep machinery of the world, you might quietly subscribe before you fall asleep. There is no hurry. We have a long, calm night ahead of us and a great deal of patient clockwork still to wander through. Because we have only just met the three wobbles by name, we have not yet sunk into how strange they truly are, nor met the patient men who first read them out of the rocks and the maths, nor reached the two great problems that still keep certain scientists awake, the puzzles, where this tidy clockwork stops being tidy and turns quietly into a mystery nobody has fully solved. All of that is waiting. For now, let us go a little deeper into the wobbles themselves, slowly, one at a time, feeling the shape of each before we let it blur into the others. Start with eccentricity, the breathing of the orbit. We think of the Earth's path around the Sun as a circle, and it nearly is, but not quite. It is a gentle ellipse, very slightly squashed, and that squashing is not fixed. Over time, the orbit stretches a little, becomes more of an oval, and then relaxes back toward a circle, and then stretches again. The measure of that stretching is eccentricity, and right now it stands at a very low value, about 1 7/10, 0.0167, which means our orbit at the moment is very nearly round. But over the long cycle it can swell to nearly 6/100, more pronounced, more of an oval, before easing back down toward almost perfectly circular, as low as around 3/1000. The whole slow swing of it carries two main rhythms, one of roughly 100,000 years and a longer, deeper one of about 405,000 years. And here is something worth resting on for a moment, because it is one of the most beautiful facts in all of this. That longer rhythm, the 405,000-year beat, is extraordinarily steady. Of all the movements in this entire system, it is the most reliable, the most metronomic. It keeps such faithful time that geologists use it as a kind of clock buried in the deep past, reading it out of the layered rock to date events tens and even hundreds of millions of years old. A heartbeat so regular that the stones themselves can be told their age by it. What drives this breathing of the orbit is not the Earth alone. It is the gentle, ceaseless gravitational pull of the other planets, and above all, the two that matter most here, Jupiter, the great heavy giant out beyond us, and Venus, our near neighbor toward the Sun. Their slow gravitational hands, tugging across the vast distances century after century, stretch and slacken the shape of our path around the Sun, the largest planet and one of the nearest between them, shaping the very ellipse the Earth travels, and through it, in the faintest way imaginable, helping to decide when the ice will come. And so the orbit breathes. But knowing that the orbit changes shape is only the beginning of the question. The real mystery, the one that took the better part of 2 centuries to even properly ask, is this: what does the changing shape of the orbit actually do to the ice? How does the gentle stretching of an ellipse, too subtle to feel, too slow to watch, reach down into the climate of this world and decide whether Toronto sits under a mile of glacial ice or under a summer sky? The answer, when it finally came, was not the answer anyone expected. And it begins with a paradox that is worth turning over slowly, because it is the kind of thing that seems wrong at first. And then, the longer you sit with it, becomes one of the most illuminating ideas in all of Earth science. Ice ages are not made by cold winters. That sentence sounds like it should be a mistake. It sounds like saying that floods are not made by rain, or that droughts are not caused by heat. But it is true, and the reason it is true is both simple and profound. Think about what actually causes ice to accumulate and stay on the land. It is not that one winter is colder than another. Cold winters come every year, even now, even in warm climates compared to the great ice ages. The question is never whether enough snow falls. In the regions where ice sheets form, snow falls abundantly through the winter months regardless of the small variations in orbital geometry. The snow is not the problem is the summer. If a summer is warm enough, long enough, fierce enough in its heat, it will melt away every last trace of the previous winter's snowfall. The land returns to bare ground, bare rock, bare soil, and when the next winter comes and the snow falls again, it is starting from nothing. There is no accumulation, no building upward from year to year. The ice sheet can never get started. But if the summer is a little cooler than usual, a little shorter, a little less direct in its heat, something different happens. The winter's snow comes down, as it always does. And then when the summer arrives, it does not have quite enough strength to melt all of it. A little remains, perhaps in a hollow, perhaps on the shaded side of a rise in the ground, perhaps simply as a thin but persistent layer across a wide expanse of landscape. A few centimeters of snow that survived the summer intact, and then autumn comes, and then winter, and new snow falls on top of the remnant from the year before, and the following summer comes again, and again it is a little too cool, a little too gentle, and again it does not quite manage to erase everything. Another thin layer survives. Year by year, this is how an ice age begins. Not with a sudden plunge into darkness, not with a catastrophic winter, but with summers that are, just barely, not quite fierce enough to do their job of melting. The ice accumulates the way a debt accumulates, slowly at first, almost imperceptibly, a little more each year that the balance tips the wrong way. And over hundreds and then thousands of years, what began as a few surviving centimeters of snow becomes meters, and then tens of meters, and then hundreds, and the great continental ice sheets are born. This is what Milutin Milankovitch understood, and it is the insight that sharpened and corrected and ultimately redeemed the whole orbital theory of ice ages. It is not winter that matters, it is summer. Specifically, it is the amount of solar energy delivered to the high latitudes of the northern hemisphere during the summer months. That is the key. That is the lock that the orbital cycles open and close over their long, patient timescales. There is a specific latitude that has become the canonical reference point for this idea, a single invisible line drawn around the globe at 65 degrees north. 65 degrees north. If you were to follow that line across the surface of the Earth, you would pass through the northern parts of Canada, through the broad expanse of central and eastern Scandinavia, through the interior of Russia, across the vast and largely empty landscapes of Siberia. This is not the Arctic itself, not the extreme north where the sun never rises in winter. This is the broad subarctic zone, the region where large continental landmasses spread out in every direction, and where, in winter, enormous quantities of snow fall and accumulate. The question that Milankovitch asked, and that the orbital cycles answer, is this: how much sunlight falls on that line at 65 degrees north during the summer months? How intense is the solar energy delivered to that particular band of latitude during the season when ice must either melt or survive? When that number is high, the summers are warm enough to scour the landscape clean, and ice sheets cannot persist. When that number is low, the summers are cool and brief, and the ice begins very slowly to gather. That single number, the summer insolation at 65 degrees north, is what the three orbital wobbles are, constantly, slowly changing. The eccentricity of the orbit affects how much total sunlight the Earth receives, and when, stretched over the year, that light is strongest. The tilt of the axis, the obliquity, determines how extreme the seasons are and how much summer light floods into the high northern latitudes. And the precession, the slow wobble of the axis, like a spinning top, losing a little of its spin, determines which season of the year falls when the Earth is closest to the Sun at that point in the orbit called perihelion. It is worth pausing on that last word because it is the key to understanding something subtle and important about where we are right now in our own time in this particular chapter of the long orbital story. Perihelion is the point in Earth's orbit where we are closest to the Sun. Aphelion is the farthest point, and because our orbit is not a perfect circle, but that very slightly stretched ellipse we have already spoken of, there is a real difference between the two. When Earth is at perihelion, it receives a little more sunlight. When it is at aphelion, a little less. The difference is not enormous, but it is real, and across the whole broad disk of the planet's surface, it adds up. Right now, in our own era, the Northern Hemisphere's winter falls near perihelion. This happens to coincide with early January, when in fact the Earth is at its closest point to the Sun, even as the northern half of the planet is tilted away from it and experiencing the cold, dark months of winter. And conversely, the Northern Hemisphere's summer falls near aphelion in July, when the Earth is actually slightly farther from the Sun than at any other point in the year. Think about what this means for the question we are asking. It means that right now the Northern Hemisphere summer receives a little less solar energy than it might, not only because of the geometry of the axial tilt, but because summer happens to fall at the moment in our orbit when we are slightly farther from the Sun. The two effects partially offset each other. The summers at 65 north are, in orbital terms, a little gentler than they could otherwise be. And this has been the situation more or less for the past several thousand years. We are, in a sense, in an era of relatively subdued northern summers, at least as far as the orbital geometry is concerned. But this was not always so, because precession changes slowly over time, the alignment of the seasons against the orbit shifts. Roughly 11,000 years ago, the situation was reversed. The Northern Hemisphere's summer fell near perihelion. The Earth was closest to the Sun in the summer months, and the summers at 65 north were correspondingly warmer, delivering more energy to the high latitudes during precisely the season when ice must melt or survive. 11,000 years ago, the orbital deck was stacked against ice formation in a way that is different from today, and that difference, gradual as it is, slow as the turning of that long precession cycle, is part of what the climate reads, what it responds to, what it translates into the advance and retreat of the great sheets of ice. Now, some of this might prompt a question that feels entirely reasonable. If the Northern Hemisphere is where the trigger is, and if Northern Hemisphere summers are the key, why is it the Northern Hemisphere? Why not the South? The Southern Hemisphere also has high latitudes. Antarctica sits at the pole. Why does the climate of the whole planet seem to hinge, in this orbital reckoning, on a line of latitude in the north and not on an equivalent band in the south? The answer lies in the geography of the planet, in the arrangement of land and ocean across the two hemispheres, and it is one of those facts that seems simple once stated, but carries enormous implications. The Northern Hemisphere contains the bulk of the world's large continental landmasses. North America stretches from the tropics to the high Arctic. Eurasia, the joined continent of Europe and Asia, sprawls across more than a third of the planet's surface at middle and high latitudes, and it is on land, not on open ocean, that continental ice sheets can form and grow. Ice sheets require a solid substrate. They require terrain that can hold the accumulated snowfall year over year and allow it to compact under its own weight into glacial ice, deepening and thickening and eventually flowing slowly outward under the pressure of its own mass. The Southern Hemisphere, at the latitudes equivalent to Canada and Scandinavia, is, for the most part, open ocean. The Southern Ocean wraps around Antarctica in an unbroken ring, and ocean behaves quite differently from land when it comes to ice formation. The ocean absorbs heat and releases it slowly, moderating temperatures. It circulates, carrying warmth from the tropics toward the poles and cold water away. Building a great continental ice sheet on open water is not possible in the way it is on land. Antarctica has its ice sheet, yes, and it is vast and ancient. But the Southern Hemisphere does not have the broad temperate and subarctic continental shelves where ice can accumulate and spread in response to small orbital nudges. So the trigger is in the north, not because of some arbitrary asymmetry in the orbital geometry, but because of the shape of the planet itself, the distribution of continents, the arrangement of land and sea that has evolved over hundreds of millions of years of plate tectonics has placed the most ice-capable terrain in the hemisphere, where the orbital signal can reach it most effectively. Nature has built the apparatus where the signal is designed to ring. It is one of the quieter wonders of this story. The ice ages of the last several million years are not simply orbital. They are the product of orbital geometry meeting planetary geography, of a slow astronomical clock ticking against a particular arrangement of continents. And the result of that meeting is the cycle of cold and warmth that shape the world we live in. But even understanding all of this, even grasping the cool summer paradox and the significance of 65 North, and the reason the continents matter, you are still only at the beginning of the story of how a small orbital nudge becomes a mile of ice. Because the orbital changes themselves are quite small, the variations in summer insolation at 65 North, driven by the wobbles of the orbit, are real, measurable and important, but they are not large enough on their own to account for the full magnitude of the ice ages. Something has to take the orbital whisper and amplify it into a roar. Something has to translate a modest shift in summer sunlight into glaciers 2 kilometers thick, covering the places where cities now stand. That something is feedback. And the most important of the feedbacks, the one that operates most immediately and powerfully in the early stages of an ice age, is one of the simplest physical processes imaginable. Snow is white, ice is white, and white surfaces reflect sunlight. This seems almost too obvious to be significant, but its implications, when you follow them through, are staggering. Consider what happens when a cool summer allows a little extra snow to survive the season and remain on the ground as autumn approaches. That snow is white. When the next year's sunlight arrives, some of what would have warmed the bare, dark soil instead bounces off the white surface and goes back out into space, unused, unconverted into heat. The ground beneath is insulated, staying colder. The air above is less warm than it would have been over bare ground. And as the temperatures stay a little lower, conditions become a little more favorable for the next winter's snowfall, to begin a little earlier, to last a little longer, to lie a little thicker. This is what scientists call the ice albedo feedback, and it is one of the great amplifying engines of the climate system. Albedo is simply the measure of how reflective a surface is, how much of the incoming sunlight it sends back rather than absorbing. Fresh snow has an albedo approaching 90%. It reflects nearly all the light that strikes it. Dark open ocean has an albedo of around 6%. It absorbs nearly everything. The difference between a landscape covered in ice and the same landscape bare and dark is almost incomprehensibly large in terms of how much solar energy each surface captures. So as the ice sheet begins to form and grow, it creates a self-reinforcing condition. More ice means more reflectivity, which means less absorbed solar energy, which means cooler temperatures, which means more ice survives each summer, which means even more ice. The feedback runs in a loop. The climate system, pushed into a slightly cooler state by the orbital geometry, begins to amplify its own cooling. What started as a small external signal, a modest reduction in summer insolation at 65 North, is picked up by this internal mechanism and turned into something far more powerful. Think of it like this. Imagine you are trying to heat a room and someone has left a window open just a crack, not wide, just barely ajar. The heat seeping out through that crack alone would not make the room cold. But if the slight drop in temperature causes frost to form on the windowsill, and that frost reflects the sunlight that would have warmed the floor, and the floor stays cooler, and that encourages more frost to form further across the glass, you can see how the system might begin to pull in a direction that amplifies the original small perturbation. The window was never thrown wide open, but the room grew cold anyway because the system found a way to run the cooling forward on its own momentum. The ice albedo feedback is the climate system doing something similar, but on a continental scale over thousands of years. The orbital nudge opens a small window, the albedo feedback flings it wide, and the ice albedo feedback is not the only amplifier at work. There are others operating on longer timescales and through different pathways. One of the most important involves the oceans and the atmosphere, and specifically the behavior of carbon dioxide. When the climate begins to cool, the oceans play a complicated and still not fully understood role. Cold water dissolves gases more readily than warm water, the way a cold fizzy drink holds its carbonation longer than a warm one. As the surface waters of the ocean cool during the early stages of glaciation, they are able to absorb more carbon dioxide from the atmosphere. Carbon dioxide is drawn down from the air and dissolved into the sea. And since carbon dioxide is one of the most important greenhouse gases, the gas that, along with water vapor, keeps the planet warm by trapping outgoing heat radiation, reducing the amount of it in the atmosphere, causes additional cooling. This is the CO2 feedback, and it works in the same direction as the ice albedo feedback, amplifying the initial orbital signal rather than counteracting it. The orbit nudges the temperature down. The ice albedo feedback amplifies the cooling locally. The CO2 feedback then deepens the cooling globally because the atmosphere is shared by the whole planet. What begins as a Northern Hemisphere summer problem becomes, through these chains of connection, a worldwide climate shift. The oceans also change their circulation as the climate cools, with deep currents that carry heat around the planet, rearranging themselves in response to the shifting temperature gradients and the growing presence of cold, dense water sinking near the poles. Ocean circulation is like a vast conveyor belt moving heat from the tropics toward the poles and carrying cold water back along the bottom, and when that belt changes speed or direction, the effects ripple out across the whole planetary climate. This is another amplifier, another way the system takes the orbital signal and runs with it beyond what the signal alone would produce. All of these feedbacks, the ice albedo, the CO2 drawdown, the ocean circulation shifts, are what transform the quiet astronomical whisper into the full-throated roar of a glacial age. The orbit provides the timing. The orbit sets the rhythm, the beat, the tempo of when cool summers arrive and when warmer ones follow. But the amplitude, the actual depth and cold of the ice ages, the 2 kilometers of ice, the temperatures 6 to 8 degrees Celsius, colder than today, across global averages, that comes from the Earth system's own internal amplifiers, which take the orbital nudge and multiply it through feedback and connection until a moderate change in summer sunlight becomes one of the most dramatic climate states the planet can reach. This distinction matters deeply, and it is one that popular accounts of Milankovitch cycles often pass over too quickly. The orbit does not power the ice ages, it paces them. Think of the difference between a conductor and an orchestra. The conductor does not make the sound. The sound comes from the musicians, from the instruments, from the resonance of the hall. But the conductor sets the tempo, gives the downbeat, tells the whole ensemble when to begin and when to rest. The orbit is the conductor. The climate feedbacks are the orchestra, and together they produce something far larger and more powerful than either could generate alone. Now, there is something else that Milankovitch recognized, or rather, something that his work made possible for others to recognize later, about the relationship between the 3 orbital cycles and the trigger at 65 north. The 3 cycles do not operate independently in their effect on northern summer insolation. They interact. They combine and interfere with one another the way ripples on a pond combine and interfere, sometimes adding together and sometimes cancelling out. Consider what happens when the tilt of the axis is at its maximum, around 24.5 degrees, while at the same time the precession cycle has aligned so that the northern hemisphere summer falls near perihelion. These 2 effects reinforce each other. The high tilt means the northern hemisphere is leaning strongly toward the sun during summer, receiving more intense sunlight at high latitudes. And perihelion means the Earth is also at its closest point to the sun during those same summer months. Both effects are pushing in the same direction. The result is a summer at 65 north that is significantly warmer than average, and the conditions for ice accumulation are correspondingly poor. But now consider the opposite case. The tilt is near its minimum around 22 degrees, and Precession has arranged things so that the northern hemisphere summer falls near aphelion, with the Earth at its farthest from the Sun during the very season when high northern latitudes depend on solar energy to melt their snow. Both effects are pushing toward cooler summers. The tilt is keeping the angle of incidence low, and the orbital position is keeping the Earth at a greater distance from its heat source precisely during the critical months. These are the conditions under which ice sheets can begin to form and grow. The actual curve of summer insolation at 65 north, as calculated by Milankovitch across hundreds of thousands of years of orbital history, is not a simple, regular, sine wave. It is the superposition of several overlapping rhythms: the 100,000-year eccentricity breathing, the 41,000-year tilt oscillation, the 23,000-year and 19,000-year precession wobbles, all layered on top of one another like the voices in a slow, complex chord. Sometimes they align and reinforce, sometimes they oppose and partially cancel. The result is a ragged, irregular curve, full of variation on multiple timescales, a rhythm that is patterned but not perfectly periodic, a signal that carries deep structure within apparent complexity. And it is that signal, that complex curve of summer sunlight at 65 north, computed painstakingly by hand across 600,000 years of orbital history, that Milankovitch produced over the course of his long, patient, decades-long effort. It was the signature he offered to geology. This is what the orbit suggests the climate should have done. Here is the waveform. Go look in the rocks and the sediments and the ice and tell me whether the Earth actually followed it. For a long time, the geological record was too imprecisely dated to answer. That changed in the most decisive possible way in a particular year, with a particular paper. But that is a story for a little later. For now, rest with the image of the curve itself, that long traced line of summer sunlight, rising and falling over hundreds of thousands of years, calculated by one man with pencil and paper, carrying within it the argument that the great ice ages of the deep past were not random, not mysterious, not ungoverned, but timed by the patient mechanics of gravity and orbital geometry, timed by the interaction of three slow wobbles in the way the Earth moves and holds itself in space, translated through the geography of continents and the physics of snow and ice and gas into the succession of worlds, cold and warm, that has characterized our planet's recent history. The curve rises and the ice retreats, the curve falls and the ice advances. Summer fades at 65 north and the snow survives another year, and another, and another. The feedback loops engage, the albedo brightens, the carbon dioxide ebbs from the air, the ocean circulation shifts, and what was a small astronomical suggestion becomes, over thousands of years, a world transformed, a world of ice. And then very slowly the orbit shifts again, the tilt begins to increase, the precession turns. The summer at 65 north begins to receive a little more energy. The ice albedo feedback runs in reverse. Melting ice reveals dark ground absorbs more heat, more ice melts, the ocean warms and releases its dissolved carbon dioxide back into the atmosphere. The greenhouse effect reasserts itself, and the great ice sheets, kilometers thick and continent spanning, begin their long, slow retreat, carving into the sea, vanishing from landscapes that will not see ice again for tens of thousands of years. This is the cycle. This is what the three wobbles do together in concert, mediated by the geography of northern continents and the feedbacks of the climate system. The orbit is the metronome, setting the tempo of a planetary rhythm that has been playing for millions of years, that played long before there were human ears to hear it, and that will go on playing in some form for millions of years to come. But even now, even having traced the mechanism this carefully, there remains something deeply puzzling at the heart of this story, something that the orbital theory, for all its elegant explanatory power, does not cleanly resolve. And it is to that puzzle, that beautiful, stubborn, still unsolved problem at the center of everything, that this narration will eventually turn. For now, though, let the feedback loops run. Let the snow accumulate on the hillsides of what will one day be Scandinavia. Let the white surface spread slowly southward, year by year, decade by decade, century by century. Let the air cool and the carbon dioxide ebb, and the ocean rearrange its slow currents. Let the ice grow. It has all the time in the world. That is, after all, the nature of these cycles. Slow, patient, vast, and real. And yet the story of how any of this came to be known is, in its own way, as remarkable as the science itself. Because the idea that the Earth's orbit shapes the coming and going of ice ages did not arrive complete and polished from some well-funded observatory or grand university laboratory. It came, first, from a man who had no formal scientific education at all, who learned what he knew from books he read during his lunch breaks, who understood the movements of planets and the chemistry of climate through nothing but the sustained, quiet attention of a curious mind working in conditions that most professional scientists of his era would have found unacceptable. His name was James Croll. He was born in 1821 in a small village in Perthshire, Scotland, the son of a stonemason, and he left school at the age of 13. What followed were decades of restless, unsatisfying work, and he tried carpentry, then tea dealing, then innkeeping, then insurance, then various other trades that never quite held his interest. But through all of it, he kept reading philosophy, physics, mechanics, the literature of natural science as it existed in the mid-19th century, still largely accessible to a careful lay reader, still written in a language that did not require a university degree to follow. Croll was the kind of person who cannot stop thinking, cannot stop asking why, cannot rest in the comfortable acceptance of received ideas. He worried at questions the way a river worries at stone, patient and persistent, and entirely uninterested in taking the easy way around. By the time he was in his late 30s, a series of circumstances had placed him in a position that was, in its way, exactly right for the kind of work he would do. He had taken a job as a janitor, a caretaker, more precisely, at the Andersonian College in Glasgow, an institution that would eventually become the University of Strathclyde. The job was unglamorous. He swept floors. He kept the building. He lit fires in the cold months. But the Andersonian had a library, and James Croll had access to it, and in the hours when the floors were swept and the fires were burning, he sat and he read. It was there, in that library in the early 1860s, that he began to think seriously about the ice ages. The fact of glaciation, see that vast sheets of ice had once covered much of northern Europe and North America, had by then been established for several decades. The work of Louis Agassiz and others who had recognized the erratics and the moraines and the scratched bedrock for what they were, the signatures of ice that was no longer there. The question was what had caused it. Why had the climate swung so dramatically from the conditions of the present to something cold enough to bury Scandinavia and Scotland under ice a mile thick? The standard answers of the time were vague and unsatisfying. Croll thought he saw a better one. He had been reading about the way Earth's orbit changes over long periods of time, about the stretching and squeezing of the ellipse that traces the planet's annual path around the Sun, about the slow wobble of the axis, about the shifting geometry of the relationship between Earth and the light it receives. And something about those long, slow, rhythmic variations struck him as the right kind of cause for the long, slow, rhythmic climate changes that the geological record was beginning to reveal. In 1864, he published his first major paper on the subject. The journal was the Philosophical Magazine, and the title was on the physical cause of the change of climate during geological epochs. He was 43 years old, working as a janitor, and he was proposing a theory of ice ages grounded in celestial mechanics. The core of Croll's idea was this, that when Earth's orbit is most elliptical, when eccentricity is at or near its peak, the difference between the planet's closest approach to the Sun and its farthest point becomes large enough to matter, and that this difference, combined with the wobble of the axis, could shift enough sunlight away from one hemisphere's winter to trigger glaciation. He understood intuitively that this would not work in isolation, that some amplifying mechanism was needed to turn a modest orbital nudge into something capable of building ice sheets. And here he showed genuine insight that went well beyond the orbital geometry itself. He proposed that ice and snow, being white, would reflect sunlight back into space, that the accumulation of ice would cool the climate further, which would cause more ice, which would reflect more light, a self-reinforcing loop. He also proposed that changes in ocean circulation, in the way warm water is transported from the tropics toward the poles, would play a role in distributing or withholding heat. These ideas, the albedo feedback and the role of ocean currents, were not trivial guesses. They were the conceptual ancestors of mechanisms that modern climate science has confirmed and quantified in considerable detail. By 1875, Croll had gathered his thinking into a book. He called it Climate and Time in Their Geological Relations, and it represented the most complete and rigorous theory of ice ages that had yet been assembled. He had by this point left the janitor's position. The scientific work had brought him to the attention of the geological community, and he eventually obtained a position at the British Geological Survey. But the book was the product of those library years, that patient self-education, that solitary thinking in a building where his official duties had nothing to do with the movements of planets. And for a time, the theory was taken seriously. Geologists read it, scientists discussed it. Croll corresponded with Charles Darwin, with John Tyndall, with figures at the center of Victorian science. There was a period in the 1870s and 1880s when it seemed as if the orbital theory of ice ages might actually take hold, but then the field geology caught up with the chronology, and the chronology was wrong. This is the part of the story that requires a moment of careful attention because it illustrates something important about how science actually works, which is to say, slowly, imperfectly, with many false starts and corrections, and with a tendency to discard good frameworks when specific predictions fail, even when the underlying framework is sound. Croll had proposed, based on his calculations of eccentricity and precession, that the last great ice age had occurred roughly 80,000 years ago or more, that it had largely ended by that time, and that the world had been in a warm phase for something in the vicinity of 80,000 years. He also proposed, somewhat counterintuitively, that ice ages would alternate between hemispheres, that when orbital conditions favored glaciation in the north, they would simultaneously disfavor it in the south, and vice versa. Both of these specific predictions turned out to be incorrect. As geologists worked to date the glacial deposits they found across Europe and North America, the moraines, the outwash plains, the layers of sediment that mark the retreats and advances of the great ice sheets, the picture that emerged was not consistent with Croll's chronology. The evidence suggested that the most recent glaciation had ended far more recently than 80,000 years ago, that ice sheets had still been covering large portions of northern Europe and North America as recently as 12,000 years ago, and that the alternating hemisphere model did not match what the rocks showed. When the chronology failed, the theory failed with it. Not all at once, not immediately, but gradually, in the way that scientific ideas lose their currency when they stop making accurate predictions. By the end of the 19th century and into the early 20th, the orbital theory of ice ages was largely in eclipse. Croll died in 1890, and the idea he had spent the best years of his mind developing went with him into a kind of dormancy. Not quite forgotten, but no longer at the center of the conversation about what causes the ice to come and go. The question was, once again, open. It would take a different man from a different country, working in a different century, to pick up the thread. Milutin Milankovitch was born in 1879 in the village of Dalj in what is now Croatia, then part of the Austro-Hungarian Empire. He studied civil engineering in Vienna, earned his doctorate in 1904, and worked for several years as an engineer before accepting a position as a professor of applied mathematics at the University of Belgrade in 1909. He was, by all accounts, a precise and methodical thinker, someone who found satisfaction in long, careful calculations, in the patient accumulation of numbers toward a result that only emerges after enormous amounts of sustained effort. He had read Croll. He understood both the power of the orbital hypothesis and the nature of its failure, and he believed, with the confidence of a mathematician looking at a problem that had not yet been solved correctly, that the failure was not one of concept, but of execution. That Croll had been right to look at the orbit, right to invoke albedo feedback, right to suspect that the geometry of Earth's path around the Sun was the pacemaker of the ice ages, but had made the critical error of getting the trigger wrong. Croll had emphasized winter. He had focused on the idea that a hemisphere's winters, made more severe by orbital conditions, would allow ice to grow. Milankovitch saw it differently. He thought the critical variable was not winter cold but summer warmth, or rather the lack of it. A winter cold enough to produce snow is, in itself, insufficient to build a continental ice sheet. What matters is whether the summer that follows is warm enough to melt that snow. If summer comes with enough heat, the winter's snow disappears and the land returns to bare ground. If summer comes too gently, too moderately, the snow persists. And the following winter adds more to what the previous summer failed to remove. Year by year, the snow deepens. Decade by decade, it compresses into ice. Century by century, the ice thickens and spreads. The glacier is born not from winter's violence, but from summer's insufficient warmth. This insight, that ice ages are made by cool summers, not cold winters, shifted the entire focus of the theory, and it pointed Milankovitch toward a specific, calculable quantity, the amount of solar energy received at high northern latitudes in summer. He fixed on 65 degrees north as his benchmark, that invisible line running through the interior of Canada, across southern Scandinavia, cutting through the heart of Siberia. At that latitude, on that line, in the summer months, that was where the fate of ice was decided. If summer insolation at 65 degrees north was diminished by the right combination of orbital conditions, snow would survive the summer, and the slow machinery of glaciation would begin its long cycle. He set out to calculate it. Not with computers, there were none. Not with teams of assistants running numerical models on vast banks of instrumentation. With pencil and paper, with the mathematical tools available to a well-trained applied mathematician in the early 20th century, he set out to compute the amount of sunlight falling on each latitude of the northern hemisphere in each season for every point across 600,000 years of Earth's orbital history. The sheer scale of the undertaking is worth pausing to consider. 600,000 years. The orbit changes slowly. The eccentricity cycle runs roughly 100,000 years, the obliquity cycle 41,000, the precession cycle 23,000. So across 600,000 years, the orbital parameters go through multiple complete oscillations, combining and recombining in different ways, producing a complex, layered pattern of sunlight variation that no single cycle captures alone. To track all of this, to calculate the insolation at multiple latitudes across all of those years, required an enormous number of individual computations. Milankovitch worked at it for decades on and off, alongside his academic duties. And part of that work, a portion of it that has become one of the more celebrated images in the history of science, was carried out under circumstances that were, to put it mildly, unusual. In the summer of 1914, Milankovitch was visiting a friend in the Austrian resort town of Kecskemét when the First World War began. As a Serbian citizen living in Austro-Hungarian territory, he was immediately arrested and interned as an enemy alien. He spent the early part of his detention under conditions of genuine uncertainty, not knowing what would happen to him or for how long he would be held. But he had brought his work with him. His notebooks, his calculations, the pencil and paper computations of ancient sunlight. And in the months that followed, the story, as it has come down to us, holding something of the quality of legend, though the essential facts are documented, he continued to work, confined but not idle. Interrupted but not stopped. The celestial mechanics did not pause for the war. The orbital geometry of 600,000 years of Earth history did not care about the particular political catastrophe unfolding in the summer of 1914. And so Milankovitch sat with his notebooks in custody and calculated. He was eventually released and allowed to return to Budapest, where he continued his work under what were, by the standards of wartime, relatively comfortable conditions. The diplomatic community assisted in this, and he worked in the library of the Hungarian Academy of Sciences for much of the war, a circumstance that, whatever its hardships, gave him access to the resources he needed and the quiet necessary for sustained calculation. The war years were, in a strange way, some of the most productive of his scientific life. What he was building through those years and the decades that followed was something no one had attempted at this level of rigor before, a complete quantitative account of how the three orbital cycles, eccentricity, obliquity, and precession, combined to modulate the amount of sunlight reaching each latitude of the Earth's surface across geological time. He was translating the celestial mechanics into a climate signal, turning the abstract mathematics of planetary orbits into curves of ancient insolation, season by season, latitude by latitude. By around 1920, he had produced what he called his insolation curves, graphs showing the calculated amount of summer sunshine at various northern latitudes across hundreds of thousands of years. These curves undulated slowly up and down, their rhythms set by the overlapping periods of the three wobbles, showing the epochs of diminished summer warmth that corresponded, in his view, to the conditions that would trigger glaciation. The question was whether anyone else would take them seriously. The answer came partly through a collaboration that is worth describing because it illustrates how scientific ideas sometimes find their way into the mainstream through unexpected routes. Vladimir Köppen was a German-Russian climatologist, a towering figure in the study of climate, who is perhaps best known today for the Köppen climate classification system, the framework for describing the world's climate zones that still bears his name and is still taught in geography classrooms around the world. He was also, by the early 1920s, the father-in-law of Alfred Wegener. Alfred Wegener is, of course, the geologist and meteorologist who proposed the theory of continental drift, the idea, now fully vindicated and extended into the theory of plate tectonics, that the continents are not fixed in place but have moved slowly across the face of the Earth over geological time. In the 1920s, Wegener's continental drift hypothesis was still controversial, still resisted by significant portions of the geological establishment, and Wegener himself was a figure who combined scientific boldness with a willingness to work across disciplinary boundaries. In 1924, Köppen and Wegener, father-in-law and son-in-law, two men who had both spent their careers thinking about how the Earth's systems change over long time scales, published a book on past climates, Die Klimate der geologischen Vorzeit, the climates of the geological past. In it, they incorporated Milankovitch's insolation curves, using them as the basis for an interpretation of when and why past ice ages had occurred. They saw in Milankovitch's calculations the mathematical foundation that the orbital hypothesis had always lacked: the precise quantitative account of how the orbital cycles actually translated into changing patterns of solar energy at the Earth's surface. For Milankovitch, the collaboration was an important endorsement. Köppen's authority in the world of climatology was considerable, and Wegener's name, even then, carried weight. The 1924 book brought Milankovitch's curves to a wider audience than he had reached on his own. Milankovitch continued refining and extending his work through the 1930s, and in 1941 he published what would become his definitive statement of the theory, Kanon der Erdbestrahlung und seine Anwendung auf das Eiszeitenproblem, translated roughly as Canon of Insolation and the Ice Age Problem. It was a comprehensive synthesis running to hundreds of pages, presenting his calculated insolation curves for the past 600,000 years and arguing in systematic detail that the rhythm of ice ages could be read from the rhythm of orbital geometry. The book was published in Belgrade, in Germany, in the middle of the Second World War, under circumstances that were hardly conducive to wide scientific distribution. Milankovitch was 62 years old, and he had spent the better part of 30 years on this project. And then, in a pattern that must by now feel familiar, in the telling of this story, the theory went quiet again. Not immediately and not entirely. There were geologists who took Milankovitch's work seriously, who saw in his curves a plausible account of past climate change. But there was a fundamental problem, and it was the same problem that had undermined Croll before him, the same problem that any orbital theory of ice ages would face until a particular technological challenge was solved. The problem was dating. To test the orbital theory properly, you need to know not just that ice ages happened, but when they happened, precisely when the great ice sheets advanced and retreated, when the climate lurched from glacial cold to interglacial warmth and back again. And in the 1940s and 1950s, the tools for precisely dating geological events across hundreds of thousands of years simply did not exist, at least not in a form capable of resolving the question. Radiocarbon dating, developed in the late 1940s, could reach back roughly 50,000 years under the right conditions, but the glacial cycles Milankovitch was describing extended across 600,000 years, and the most interesting questions about the timing of glacial maxima and terminations, about the precise relationship between orbital cycles and ice advances, required resolution across that full span. Without precise dates for the climate record, there was no way to confirm or deny that the rhythm of past ice ages matched the rhythm of Milankovitch's insolation curves. You could compare the general shapes and argue for plausibility, but you could not perform the kind of rigorous spectral analysis that would either vindicate or refute the theory. The orbital hypothesis remained a promising framework in search of a test it could not yet receive. So the theory sat somewhat suspended, somewhat uncertain, not discredited in the way that Croll's specific chronological predictions had been discredited. Milankovitch's mathematics were sound, and no one had found an obvious error in his calculations. But not confirmed either, not proven, not yet converted from a plausible hypothesis into an established account of how the ice ages work. For roughly 30 years after the publication of the canon, through the 1940s, through the 1950s, into the 1960s, the orbital theory of ice ages remained in this liminal state. Present, discussed, taken seriously by some, doubted by others, but waiting for something it could not yet have. Waiting for the data that would either make it or unmake it. That data would come. It would come from the ocean floor, from sediments laid down in the darkness and cold of the deep sea over hundreds of thousands of years, from the chemistry of the tiny shells of creatures so small you could fit thousands of them on a postage stamp. It would come in the form of a ratio, a comparison between two different forms of a single element, oxygen, an element so common that we breathe it without thinking and yet capable, in the right circumstances, of serving as a thermometer for a world that no one alive has ever seen. But that is the vindication, and the vindication belongs to the next part of this story. For now, rest with the waiting. Rest with the image of Milankovitch's curves, those slow, undulating lines representing the calculated history of summer sunshine at 65 degrees north, computed by hand with pencil and paper across 600,000 years, sitting in a wartime book published in a city that was, at the moment of its publication, under occupation, read by relatively few people, waiting for the world to develop the tools to test it properly. There is something appropriate, perhaps, about the pace of all of this. The orbital cycles themselves are slow, 100,000 years for eccentricity to complete one oscillation, 41,000 for the axial tilt to swing from its minimum to its maximum and back, 23,000 for the wobble of the pole to carry winter around to where summer was. These are not events on a human timescale. They are not even events on a historical timescale. They are geological. They unfold across spans of time that make the whole of recorded human history look like a single afternoon. And the science that seeks to understand them has moved at a pace that, while faster than the cycles themselves, has nonetheless required generations of patient, careful, often frustrated effort. Croll saw the outline in the 1860s. Milankovitch refined and quantified it across the first 4 decades of the 20th century. Between them, they had assembled a framework that was, in its essentials, correct. That the rhythm of ice ages is set by the changing geometry of Earth's orbit around the Sun, mediated through the specific mechanism of summer insolation at high northern latitudes, amplified by feedbacks that the climate system provides. The core of it was right. But science does not accept frameworks because they are elegant, or because they have been computed with great care, or because the people who proposed them were clearly intelligent and serious. Science accepts frameworks when they make predictions that can be tested, and when the tests, conducted with appropriate rigor, return results that match. Elegance is a hint. Computation is a tool. What settles the question is evidence. And the evidence, the deep, unambiguous, carefully dated evidence that would settle this particular question, was still waiting to be found. It was lying on the floor of the ocean, undisturbed, accumulating year by year and decade by decade in the form of sediment layers and tiny shells, as Croll and Milankovitch lived and worked and died and were forgotten and half-remembered and argued about. The ocean was keeping its own record, patient, complete, and very, very old. There is something almost dreamlike about the way the answer was eventually found. Not by going back in time, not by somehow observing the ancient ice ages directly, but by reading the chemistry of dead organisms that had drifted to the seafloor across hundreds of thousands of years and been preserved undisturbed in the cold, dark, waiting. Foraminifera, those microscopic shelled creatures whose calcareous remains accumulate in the deep-sea sediment at a rate of centimeters per 1,000 years, were, without knowing it, constructing a continuous chemical record of the ocean's temperature and chemistry. And because the ocean's chemistry changes in predictable ways as ice builds and melts, those tiny shells were, in effect, recording the history of the ice ages in a language that would eventually be readable once someone developed the vocabulary. That vocabulary is built around oxygen. Oxygen in the atmosphere and in the water and in the shells of creatures that build their bodies from seawater comes in different forms, different isotopes, atoms of the same element with slightly different masses. The two most relevant are oxygen-16 and oxygen-18, the lighter and the heavier of the two. And here is the key. When water evaporates from the ocean, it carries the lighter oxygen-16 preferentially. Lighter molecules are slightly more likely to make the transition from liquid to vapor. The water vapor rises, travels, falls as rain and snow over the continents. When the climate cools and ice sheets grow, that water, that precipitation, that snow, is locked into the ice. It sits on the land in the glaciers, bound up in the vast continental ice sheets that can reach kilometers in thickness. And the water locked in the ice is, on average, lighter than the water it came from because it was preferentially enriched in oxygen-16, which means that the ocean, having given up its lighter water to the growing ice sheets, becomes, slowly and progressively, enriched in oxygen-18. The ratio of heavy to light oxygen in the seawater rises as the ice sheets grow and falls as they melt, and foraminifera, building their shells from the seawater around them, record that ratio. The ratio of oxygen-18 to oxygen-16 in a foraminiferal shell is a signature of the ocean chemistry at the time that shell was formed. Pull a sediment core from the deep ocean floor, slice it into layers representing different time periods, measure the oxygen isotope ratio in the foraminifera at each layer, and you have, if you can date those layers accurately, a record of how ice volume has changed over time. An ice gauge built from chemistry, read from the shells of plankton, preserving a signal laid down in the darkness of the deep ocean across hundreds of thousands of years. This is the technique, delta oxygen-18, written as D18O in the notation of isotope geochemistry, that made it possible eventually to test Milankovitch's theory properly. And the men who brought it to bear on the orbital hypothesis, who collected the cores and made the measurements and performed the analysis, would publish their results in 1976 in a paper whose title contains, in its last 4 words, the whole vindication of a century of waiting. But that moment of vindication and the mysteries that the vindication revealed, those belong to what comes next. For now, the theory is still waiting. Milankovitch's curves exist on paper, computed by hand, checked and rechecked across 30 years of methodical effort. The ocean is still accumulating its record in the dark, and somewhere in the sediment archives of the deep sea, the answer is already there, written in the shells of creatures no one has yet brought to the surface to read. That is where this part of the story ends. In the patience of the waiting, in the slow accumulation of the evidence, in the long, quiet interval between the theory and its proof. The orbit is turning, as it always has. The tilt is changing, degree by degree, across its 41,000-year arc. The wobble of the pole is carrying the seasons slowly around their long precessional cycle. The 3 rhythms are playing, as they have played for millions of years, their overlapping tempos producing that complex, layered pulse that Milankovitch spent his working life computing. And the ice is doing what the ice does, building where the summers are cool enough to let it, retreating where the warmth returns, patient and indifferent, and entirely unconcerned with the question of whether any particular scientist has yet worked out the mathematics of its coming and going. The paper appeared in the journal Science in December of 1976. Its title was Variations in the Earth's Orbit, Pacemaker of the Ice Ages, and its authors were James D. Hayes, John Imbrie, and Nicholas Shackleton. 4 words at the end of that title, Pacemaker of the Ice Ages, contained, in compressed form, the answer to a question that had occupied serious scientific minds since a self-taught janitor in Glasgow first glimpsed it more than 100 years before. The method they used to reach that answer is worth pausing over because it is one of the more quietly astonishing things that science has managed to do. The question was about the past, the deep past, the last several 100,000 years of Earth's climate history. And the problem had always been that no one could read that history with sufficient precision. Croll had the theory, but the wrong dates. Milankovitch had the mathematics but no independent record of ice volume against which to check them. What Hayes, Imbrie, and Shackleton had that their predecessors had lacked was a way of looking directly into the ocean floor and reading the ancient climate there, the way a doctor reads a pulse. The method depends on foraminifera. Foraminifera are tiny marine creatures, plankton essentially, though with shells, that have lived in the ocean's surface waters for hundreds of millions of years, and when they die, they sink, slowly, through the water column and come to rest on the seafloor, where they accumulate layer upon layer in the sediment, building up a record of the ocean's conditions at the time they lived. There are vast archives of this material on the ocean floor, and beginning in the mid-20th century, oceanographers developed the technology to extract long cylindrical cores of that sediment from the bottom, pulling up column after column of compressed history, each centimeter representing thousands of years. The chemistry of those tiny shells is what makes the whole thing work. It depends on oxygen. Oxygen comes in two varieties that matter here: the lighter isotope, oxygen-16, and the heavier one, oxygen-18. The ratio of those two isotopes in the ocean's water is not constant over time. When the planet cools and ice sheets grow, something subtle but measurable happens. Water molecules built around the lighter oxygen-16 evaporate more easily, travel through the atmosphere, and tend to fall as snow at high latitudes, where they get locked into the ice. The ocean, losing its lighter water to the ice, becomes fractionally enriched in the heavier oxygen-18. When the ice melts and the fresh water returns to the sea, the ratio shifts back. The foraminifera, building their shells from the ocean water around them, record that ratio. Their shells carry the isotopic signature of the ocean at the time they lived. So a shell laid down during a cold glacial period, when ice sheets were thick and the ocean was enriched in oxygen, 18 carries a heavier signature than a shell laid down during a warm interglacial. By measuring the ratio of oxygen-18 to oxygen-16 in the foraminifera from different depths in a sediment core, you can reconstruct the history of global ice volume across hundreds of thousands of years. Not perfectly, not with the kind of precision a laboratory thermometer provides, but well enough to see the rhythm. This is what the notation D18 refers to when it appears in the scientific literature, the departure of the oxygen-18 to oxygen-16 ratio from a standard reference value expressed in parts per thousand and used as a proxy for the size of the global ice sheets and, by extension, for global temperature. It is a measure written in the chemistry of shells that spent their brief lives floating in ancient seas, creatures so small they are invisible to the naked eye, carrying in the fabric of their bodies the record of whether the world was warm or cold when they were alive. There is something in that worth sitting with for a moment. The idea that the history of the ice ages is not written in stone or in the ice itself, but in the shells of ocean plankton, drifting down through the dark water, accumulating patiently on the seafloor over thousands of centuries. Hayes, Imbrie, and Shackleton analyzed cores from the southern Indian Ocean, measuring the D18O signal through hundreds of thousands of years of accumulated sediment. And then they did something mathematically elegant. They applied a technique called spectral analysis to the climate record those cores revealed. Spectral analysis is a way of decomposing a complex, fluctuating signal into its component frequencies, of asking, in effect, what rhythms are hidden inside this complicated wave. You apply the same technique when you use a prism to split white light into its component colors, except here the prism is mathematics and the light is the jagged, up and down record of ancient ocean chemistry. What the spectral analysis found in the sediment core record was this: the climate signal, the record of ice advance and retreat encoded in the oxygen isotopes, contained clear, strong peaks at 3 frequencies: one at roughly 100,000 years, one at roughly 41,000 years, one at roughly 23,000 years, with a companion at roughly 19,000 years. Not approximately those periods, not in the general vicinity, at those periods with a precision that was unmistakable. The climate of the Earth through hundreds of thousands of years had been pulsing at the same frequencies as the three orbital cycles: eccentricity, obliquity, precession. The theory was proven, or rather, and this distinction matters and we will return to it. The timing of the theory was proven. The orbit is the pacemaker. That last word in the title is chosen with precision. A pacemaker sets the rhythm of a heartbeat. It does not supply the heart's energy. The orbit sets the rhythm of the ice ages. It does not supply their force. The proof was a proof of timing, of correspondence, of cadence. It was not, and this is important, a proof that the orbital forcing alone was sufficient to explain the size of the glacial cycles. That question, the question of where the amplitude comes from, was to remain considerably more complicated. But the skeleton of Milankovitch's vision was confirmed. The ice ages marched to the beat of the orbit, the planet's tilt, its wobble, the shape of its path around the Sun. These are not decorative astronomical facts. They are the governing clock of the planet's great cold cycles. A janitor in Glasgow had glimpsed this in 1864. A Serbian engineer had computed it by hand across 3 decades. And in 1976, the shells of ancient plankton, brought up from the floor of the southern Indian Ocean in a core of compressed sediment, confirmed it. The waiting was over. And yet the confirmation opened immediately a new and more troubling question, a question that has not been resolved in the nearly 50 years since that paper appeared, and that sits at the center of current paleoclimate research like an elegant, maddening puzzle box. The problem is this. Look at the 3 orbital cycles and the climate signal they leave in the record. The obliquity cycle, at roughly 41,000 years, has a period in the right range and an insolation effect, the change in the tilt of the axis, and what that does to the distribution of sunlight across latitudes. That is genuinely substantial. The precession signal at roughly 23 and 19,000 years similarly has a real, measurable effect on how much summer sunlight reaches the high northern latitudes. These 2 cycles leave fingerprints in the climate record that are proportionate to their forcing. The signal amplitude in the climate data is roughly what you would expect, given how much those cycles actually change the insolation at high latitudes. And then there is eccentricity, the roughly 100,000-year cycle in the shape of Earth's orbit. And here the puzzle begins. Eccentricity as an orbital forcing is genuinely weak. When Earth's orbit stretches from its current mild ellipse, currently at an eccentricity value of about 0.0167, not far from circular, toward its more elongated configurations, the total amount of sunlight reaching the planet changes by only about 0.1%. That is a tiny change. The precession cycle, by comparison, redistributes existing sunlight far more dramatically across seasons and hemispheres. Obliquity changes the gradient of sunlight from pole to equator much more significantly than eccentricity changes the total. By any straightforward accounting of orbital forcing, eccentricity at 100,000 years should be the quietest voice in the choir. But it is not. For the last 800,000 years or so, the climate record is dominated by the 100,000-year cycle. The big ice ages, the great glaciations during which ice sheets, kilometers thick, spread across North America and Eurasia, during which sea level dropped by 100 meters or more as water was locked up in ice, during which the planet was transformed from pole to equator. Those great cycles have been arriving roughly every 100,000 years. The record shouts at the frequency where the orbital signal is barely a whisper. This is the 100,000-year problem, and it is one of the genuinely unsolved puzzles in Earth science. It is not a question at the margins. It is not a minor discrepancy. It is the central oddity of the Ice Age system. The weakest orbital forcing produces the strongest climatic response, and no one has yet produced an explanation that commands complete consensus. There are proposals, several of them serious, and it is worth dwelling on them here because they illuminate how the system actually works. Or rather, how it might work, which is a different and more honest statement. One proposal involves nonlinear feedbacks. The climate system is not a simple mechanism that receives an orbital signal and outputs a proportional response. It is a vast, interconnected system of ice sheets, oceans, atmosphere, vegetation, and carbon reservoirs, all of which interact with one another in ways that can amplify small inputs far beyond their original size. A weak orbital forcing at the 100,000-year period might, under the right conditions, get caught and amplified by some resonant mode of the climate system. The way a gentle push at just the right frequency can set a massive pendulum swinging. The orbit whispers, the Earth shouts back. The problem with this explanation is identifying precisely what the resonant mechanism is and why it produces a 100,000-year response rather than some other period. Another proposal involves carbon dioxide. CO2 is a powerful amplifier of climate change. It absorbs outgoing infrared radiation and warms the atmosphere, and the geological record shows that CO2 concentrations rise and fall in rough correspondence with the glacial cycles. During the warm interglacials, CO2 is relatively high. During the cold glacials, it is lower. The CO2 changes are not the primary cause of the orbital pacing relationship, but they are an amplifier, a feedback that takes the initial orbital nudge and magnifies it. Some researchers have proposed that the 100,000-year dominance is connected to the way CO2 cycles interact with the longer eccentricity rhythm, though the precise mechanism remains a matter of active investigation. And there is a third idea related to the ice sheets themselves. When ice sheets grow very large, when they persist through multiple obliquity cycles, building thickness and extent over tens of thousands of years, they reach a kind of threshold state in which they become capable of rapid, catastrophic collapse. Under this view, the 100,000-year glacial cycles are not straightforwardly paced by the eccentricity forcing at all. Instead, they arise from the internal dynamics of large ice sheets. The orbit nudges the climate, the ice sheet builds slowly across several obliquity cycles, and then, when some threshold is crossed, the sheet collapses catastrophically, a glacial termination, and the cycle resets. The 100,000-year period emerges not because the 100,000-year orbital signal is strong, but because it takes roughly that long for the ice to build to the collapse threshold. The orbit provides the rhythm section, but the ice sheet provides the drama. None of these proposals is fully satisfying. All of them may contain partial truths. The 100,000-year problem remains open, genuinely open, in a way that a straightforward reading of Milankovitch's vindication might lead you to overlook. The orbit is the pacemaker, yes. But pacemakers set the timing of a heartbeat. They do not explain everything about how the heart works. And this is perhaps where the deepest wonder of the Ice Age system lives. Not in the settled parts of the theory, not in the clean correspondence between orbital periods and climate frequencies that Hayes, Imbrie, and Shackleton demonstrated in 1976, but in the places where the correspondence breaks down, where the system behaves in ways the orbital forcing alone does not explain, where the Earth seems to be doing something of its own. The most dramatic example of this is what scientists call the mid-Pleistocene transition, and it is a thing that rewards slow consideration because it is genuinely strange. For most of the Pleistocene epoch, for the first roughly half of the Ice Age interval that the Pleistocene represents, The climate record shows glacial cycles pacing primarily at the obliquity period of 41,000 years. The glaciations were smaller and more frequent. The climate oscillated on a roughly 41,000-year beat, advancing and retreating in rough correspondence with the obliquity forcing, the changes in the Earth's axial tilt, which is, as you would expect, a plausible primary driver, given that obliquity significantly affects the distribution of sunlight between low and high latitudes. Then beginning somewhere around 1.25 million years ago and playing out across several 100,000 years until roughly 700,000 years ago, something changed. The climate record shifted, the 41,000-year beat faded, and the 100,000-year cycle rose to dominance. The glaciations became larger, longer, and more severe. The ice sheets grew bigger before collapsing. The climate started keeping a slower, more dramatic rhythm. This interval, from roughly 1.25 million to 700,000 years ago, is called the mid-Pleistocene transition. And here is the thing that makes it so philosophically interesting, so quietly disorienting. Nothing changed in the orbit. The orbital forcing during and after the mid-Pleistocene transition is the same as it was before. The obliquity cycle kept its 41,000-year period. The precession cycles kept their 23 and 19,000-year periods. The eccentricity cycles kept their 100,000 and 405,000-year periods. The sky did not change. The geometry of Earth's path around the Sun, the angles and wobbles that Milankovitch spent his career computing, continued their stately, indifferent clockwork without interruption. 1 million years ago, the orbit was keeping exactly the same time it keeps today. But the Earth's response changed. The climate system, receiving the same orbital input it had received before, began producing a different output. The pacemaker kept its beat, and the heart started dancing to a different rhythm. Something happened down here, inside the Earth's own systems, that altered how the climate responded to the forcing it was already receiving. What changed? This, again, is a matter of ongoing investigation, and the honest answer is that no one knows with certainty. But the leading hypothesis involves something that sounds almost mundane: soil. Specifically, the deep layer of loose, unconsolidated rock material, called regolith, that underlies the ice sheets. In the early part of the Pleistocene, the subcontinent scale areas where ice sheets formed, northern North America, Scandinavia, much of northern Eurasia, were underlain by a thick layer of regolith, the accumulated product of millions of years of weathering. This loose, soft material acts as a lubricant between the ice and the bedrock beneath. Ice sheets resting on regolith can flow and slide relatively easily. They cannot build to extreme thicknesses. They are, in a sense, inherently unstable, prone to spreading out rather than stacking up. The regolith hypothesis proposes that across hundreds of thousands of years of repeated glaciation, the advancing ice sheets gradually scraped away this loose material, carrying it south as glacial deposits and exposing the hard bedrock beneath. As the regolith was progressively removed, a process that would have taken many glacial cycles and a very long time, the ice sheets began to rest on harder ground. Resting on hard bedrock, they could build to greater thicknesses. Greater thickness means greater mass, greater internal pressure, greater stability against melting, and ice sheets that can build to greater thickness before collapsing would naturally produce longer, larger glacial cycles. Cycles on the 100,000-year timescale rather than the 41,000-year one. Under this hypothesis, the mid-Pleistocene transition is a story about the slow modification of the landscape by the ice itself. The ice changed the conditions of its own formation over geological time until it crossed a threshold into a new mode of behavior. The orbit kept perfect time throughout, but the planet's response to that time evolved gradually through the accumulation of geological change until a different kind of ice age became possible. Declining atmospheric CO2 across the same interval is also implicated in the transition, a long-term cooling trend that may have progressively primed the system for larger glaciations. These factors may not be alternatives but accomplices working together across a span of time that makes human civilization look like an afternoon. The mid-Pleistocene transition is one of those scientific observations that repays quiet contemplation. It tells us that the Ice Age system is not a simple mechanism. The orbit is not an engine that turns and produces ice ages as a mechanical output. It is more like a conducting baton. It sets the tempo, it cues the entrances, but the orchestra brings its own sound, its own dynamics, its own accumulated history of practice and condition. And sometimes, apparently, the orchestra changes its instrumentation while the baton keeps its rhythm, and the music that emerges is transformed. There is another stabilizing force in the Ice Age system that deserves mention here, one that operates not at the scale of thousands of years but at the scale of geological eons, and whose influence is so pervasive it is easy to overlook. That force is the Moon. Earth's obliquity, the tilt of its axis, oscillates between roughly 22.25 degrees and 24.5 degrees over the 41,000-year cycle. That is a relatively narrow range. The tilt varies, but not catastrophically. The seasons grow more extreme and then ease back, but the planet's geometry remains fundamentally stable enough to permit the kind of regular, moderate Ice Age cycles that the paleoclimate record shows. This stability is, in significant part, a consequence of the Moon's existence and its gravitational relationship with Earth. The Moon, massive as satellites go, exerts a stabilizing torque on the Earth's rotational axis, a gyroscopic steadying effect that prevents the tilt from wandering freely under the influence of the gravitational pulls of the other planets. Without the Moon, models suggest that Earth's axial tilt could vary chaotically and dramatically, swinging not through a gentle 2-degree range, but potentially through tens of degrees or more over timescales of millions of years. The comparison case often cited is Mars, whose obliquity has apparently swung through an enormous range. Some estimates suggest tens of degrees of variation, producing wild swings in seasonal intensity that make Earth's measured Ice Age cycles look like the ticking of a well-regulated clock. The Ice Ages, then, are partly a gift of the Moon. The gentle, regular cycling of the tilt, the civilized wobble between 22 and 24.5 degrees, is possible because a large satellite happened to form in Earth's early history and happened to end up in an orbit that stabilizes the spin axis of the planet it accompanies. The Moon is not a romantic accident. It is, among other things, a planetary stabilizer, and without it the Earth's climate history might have been far more violent and far less hospitable. And then there is the 405,000-year eccentricity cycle, the longer of the two eccentricity periods, slower and more majestic than the 100,000-year one, driven primarily by the gravitational interaction of Jupiter and Venus with Earth's orbit. This cycle is, by the standards of the inner solar system, exceptionally stable. While the 100,000-year eccentricity cycle can shift somewhat in its period and amplitude across geological time, the 405,000-year cycle maintains its regularity with a precision that has made it extraordinarily useful to geologists working on timescales far beyond the reach of ice cores or ocean sediment cores. The orbital cycles can be computed backward in time, modeled using the laws of gravitational dynamics, but only up to a point. The inner solar system, it turns out, is not perfectly regular. The orbits of the inner planets are weakly chaotic, in the technical sense that tiny uncertainties in their current positions grow exponentially over time, making precise predictions impossible beyond a certain horizon. For the 405,000-year eccentricity cycle, that horizon is estimated at around 50 million years. Beyond 50 million years in the past, the chaos of the inner solar system's gravitational interactions blurs the calculation beyond reliable use. Within 50 million years, the 405,000-year cycle is stable enough to serve as a kind of deep-time metronome, a reference frequency against which geologists can calibrate the ages of rock strata laid down long before the existence of foraminifera or ice sheets. This is a remarkable use of orbital mechanics. The same gravitational physics that governs the slow stretching and relaxing of Earth's orbit today also leaves its signature in sedimentary rocks hundreds of millions of years old, in the cycling of carbonate layers, in the rhythms of ancient lake deposits, in the fluctuating chemistry of long-vanished seas. By matching those rock rhythms to the computed 405,000-year beat, geologists can date those ancient strata with a precision that would otherwise be unattainable. The orbit is not just the pacemaker of the ice ages, it is, in its stable frequencies, one of the primary clocks of deep geological time. And we come now to the present moment, or rather to the interval we presently inhabit, and what the orbital cycles suggest about its future. We are in the Holocene. The Holocene began roughly 11,700 years ago, when the last great glaciation ended and the ice sheets that had covered northern North America and much of Eurasia retreated northward. The Laurentide ice sheet, which at its maximum had buried the landscape under as much as 3 to 4 kilometers of ice, melted back. Sea levels rose, the climate warmed. The world in which human civilization developed, its agriculture, its cities, its recorded history, is a world shaped by the warmth of this interglacial. By the reckoning of the orbital cycles, the Holocene is a warm pause in the ongoing rhythm of glaciation and deglaciation. Interglacials are not permanent states. They are the brief intervals of warmth between the long, cold stretches, and the orbital forcing that sustains them eventually tips back toward conditions favorable for ice growth. The question of when the current interglacial might end, when the orbital alignment might again favor the accumulation of ice at high northern latitudes, is one that orbital calculations can address, at least approximately. The current orbital situation is, in certain respects, unfavorable for glaciation in the near future. Earth's eccentricity is presently low, about 0.0167, closer to the circular end of its range, which means the variation in Earth-Sun distance across the year is modest, and the precession cycle's effect on seasonal insolation is correspondingly muted. Low eccentricity reduces the amplitude of the precession signal. Some calculations have suggested that the combination of the current low eccentricity and the orbital geometry of this particular interglacial makes the next natural glacial onset unusually distant, potentially tens of thousands of years away under purely orbital forcing. But the orbital calculation is no longer the whole story, or perhaps even most of it. Atmospheric CO2 has risen sharply since the Industrial Revolution, driven by the burning of fossil fuels, and that rise has fundamentally altered the radiative balance of the atmosphere in ways that have no orbital analogue. Many scientists argue that the anthropogenic increase in greenhouse gases has shifted the baseline of the climate system far enough from the orbital forcing equilibrium that the next glacial onset has been significantly delayed, or possibly, under some scenarios, prevented entirely for a very long span of time. This is an active area of research, and the confidence with which any specific claim can be made is limited. The interaction between orbital forcing and anthropogenic warming is complex, and the precise future trajectory of atmospheric CO2 is unknown. But the broad direction of the argument is this. For millions of years, the timing of ice ages has been set by the patient, in different clockwork of the orbit. And now, for the first time in that long history, a process originating on the Earth's surface, but the release of stored carbon through human industry, may have inserted itself into that clockwork as a countervailing force. The pacemaker is still running, but something new has been added to the circuit. There is a specific kind of stillness that comes from holding this in mind. Standing somewhere under an open sky tonight, you are on a planet whose axial tilt is currently about 23.5 degrees and very slowly decreasing, moving toward the lower end of its 41,000-year range. The orbit is very close to circular, at low eccentricity of 0.0167, and the slow 100,000-year stretching cycle is carrying it very gradually towards slightly more elongated configurations in the future. The precession of the axis is quietly repositioning the seasons relative to perihelion, turning the great slow wheel that in roughly 13,000 years will bring the northern hemisphere summer back around to the near side of the orbit again. All three cycles are running simultaneously, as they have run for billions of years, their overlapping tempos producing that complex layered rhythm that Milankovitch spent his working life computing by hand, with a pencil, in Budapest, and in the internment camp in Osijek during the First War. The foraminifera are still sinking. Somewhere in the surface waters of the ocean, tiny creatures are building their shells from the chemistry of the water around them, recording in the ratio of their oxygen isotopes the temperature of the sea and the volume of the ice, adding their bodies to the millennia of accumulation on the seafloor, writing another line in the archive that Hayes and Imbrie and Shackleton learned to read. The archive continues, the record grows, and the 100,000-year problem remains open. The orbital signal whispers, the climate shouts. The precise mechanism of amplification, the nonlinear feedbacks, the ice sheet dynamics, the carbon cycle resonances, the interplay of forces that translates a 0.1% change in total insolation into a glaciation that buries half a continent, is still being worked out in research groups from Cambridge to Boulder to Bern by scientists who build on the work of Shackleton and Imbrie, who built on the work of Milankovitch, who built, in his turn, on the foundational intuition of a self-taught man who worked as a janitor in a museum in Glasgow in the 1860s and looked up at the sky and asked whether the geometry of the orbit might hold the answer to the coming and going of ice. That is the arc of the story. From Croll's quiet library reading to Milankovitch's patient pencil computations to the ocean sediment cores and the spectral analysis of 1976 to the open, ongoing investigation of the mid-Pleistocene transition. It is an arc that spans 1.5 centuries of human effort, and it ends not with a closed book, but with a deepened mystery. A system that is real, measurable, partly explained, and still, in its most fundamental amplitude, not fully understood. This is perhaps the most honest thing that can be said about the Ice Ages. We know the pacemaker. We have measured its frequencies in the shells of ancient plankton and found them there, exactly where the theory said to look. We know the trigger, the cool northern summer at 65 degrees north, the latitude that quietly governs the planet's ice. We know the feedbacks that amplify the orbital whisper into the full-throated rhythm of glaciation and deglaciation. We know that the mid-Pleistocene transition happened, that the Earth changed its response to an unchanged forcing, and we have ideas about why, though none of them is settled. We know that the Moon holds the tilt steady, and that without it, the climate might be far more wild. We know that the 405,000-year eccentricity cycle is steady enough to date ancient rock, and that beyond 50 million years the inner solar system's chaos blurs all calculations. What we do not fully know is why the weakest signal became the loudest voice. The 100,000-year problem sits at the center of the field, patient and unresolved, the way certain questions sit at the center of any great inquiry. Not as a failure of understanding, but as the sign that the understanding so far achieved is genuinely deep. You only reach the hard problems by solving the easy ones first. The orbit turns. The tilt shifts. The wobble carries the seasons slowly around their long cycle. And somewhere beneath the ice that still remains, in Greenland, in Antarctica, in the mountain glaciers that are presently retreating. The record of all the past cycles is preserved, core by core, layer by layer, the chemistry of ancient atmospheres and ancient temperatures written in the ice itself, waiting to be read by future researchers asking questions we have not yet thought to ask. If this story has settled anything in you tonight, this long, slow descent through orbital mechanics and ocean chemistry, and the patient calculations of forgotten scientists, then let it settle fully. Let the three wobbles continue their turning in the background of whatever rest is coming for you. The eccentricity, barely perceptible, carrying the orbit between almost round and mildly elliptical across 100,000 years. The obliquity, steady in its 41,000-year arc between 22 degrees and 24.5, holding the seasons in their measured proportion. The precession, slow and stately, walking the pole in its great cone across 25,000 years, turning the calendar of the cosmos. They will still be running when morning comes. They were running before any human looked up and noticed them. A janitor in Glasgow noticed first in the 1860s and wrote it down in a philosophy journal and was not believed. A Serbian engineer recomputed it across 3 decades and a world war and was not believed either, not for a long time. And then the shells of ancient plankton brought up from the ocean floor in a tube of compressed sediment said, yes. The orbit is the pacemaker. The timing is there, exactly where it was predicted to be. The mystery that remains is not a failure. It is an inheritance. The gift of a question real enough to outlast the answering of the smaller questions around it. The orbit whispers, and the ice ages answer. And in the space between the whisper and the answer there is still room for decades of patient inquiry, for researchers who will spend their working lives the way Milankovitch spent his, computing and checking and computing again, following the slow clockwork wherever it leads. If you are somewhere quiet now, perhaps in bed, perhaps already half inside the long dark of sleep, tell me, if you like, where in the world you are. I would genuinely like to know. The comments will be there in the morning, and I read them, every one. There is something fitting about knowing where, across the planet's turning face, these slow stories are received. Which latitudes, which longitudes, which particular spots on the 65-degree line or above it or below it, lying still while the orbit turns and the tilt shifts and the precession wheel moves its one imperceptible degree. More stories like this one are here, waiting. The same slow pace, the same long, careful attention to things that unfold across timescales that make a human life look brief. They will be there whenever you want them. For now, the three wobbles are still turning. The ice is doing what the ice has always done. The foraminifera are sinking. The sediment is accumulating. The record grows, layer by quiet layer, in the dark of the ocean floor. You have done enough for one night. Put down whatever remains of the day. Lectures over, even the professor sleeps. Good night.